Hello everybody. In this video, we're going to be going over the definition of, like what a manifold is, and then we're going to be covering our first examples. Some of which you may have seen before, some may be new. But regardless, so let's get into it. So our first definition is going to be starting off with what a manifold actually is. And I feel like manifold is one of those words that gets thrown around there, maybe in like the sense of like popular media or sci-fi, that sort of thing, where it's like the same thing with like quantum physics, where it just gets thrown into the plot of some movie and it's just like made out to be something that's a little more up there than it really is. And you'll see there are really just some natural examples of manifolds. But anyway, so we'll start off with a differentiable N manifold, where N is going to be the dimension. So this is the dimension of the manifold. So it is a set M, which is the and the book I'm using uses finite or countable union, and this is, I guess, more of like a set theory restriction from like having uncountable unions, but it's a union of charts U. We'll denote them U sub Q, which have local coordinates x1 all the way to xn, making the chart UQ identifiable with a region of n-dimensional Euclidean space. A region of Rn. Alright. And further, so this isn't the full definition. Furthermore, on each non-empty intersection of charts, so if you have UP and UQ and their intersection is not empty, so remember this is the symbol for the empty set, then essentially we have two coordinate systems on the same set, right? Because UP has its own coordinate system, which are the XP's, and UQ has its own coordinate system. So we have two different coordinate systems. And essentially the main idea of a manifold is that you're covering it with these charts U, and whenever two charts interlap, we have to be able to transfer from one coordinate system to another in a suitably nice mathematical way. And so in particular, we want the transition functions so we'll denote it like this. So let's say we write the the xp coordinates as a function of the coordinates on UQ are 1 to 1 and differentiable. And in particular, we can say that the determinant of the matrix which is formed by the partial derivatives. So in other words, the Jacobian of the transition functions. So here, this is an n by n matrix, which are indexed by alpha and beta, which are just, so it's running across the coordinates xp and xq. This determinant, the determinant of that matrix, must be non-zero on up intersect uq. So that's the definition of a differentiable N manifold. And furthermore, the general smoothness class of the transition functions which means essentially how many times can we smooth, I guess I should say, how many times can we continuously differentiate? So for instance, I forgot to take an example, but we know that a differentiable function has to be continuous, right? So differentiable implies continuity, continuous, but the derivative, we can take a derivative of a differentiable function, and that derivative may not be continuous. Right? So essentially the smoothness class is saying how many times can we take derivatives and the derivatives are still continuous. That's what this means. So the general smoothness class of the transition functions is the smoothness class of the manifold. And so in particular, throughout the series, we're essentially going to be assuming that our manifolds are essentially as smooth as we need them, right? So if we have a proof that's using second derivatives, then we're going to be assuming that those second derivatives are continuous, right? And a lot of the basic examples are going to be smooth in the sense that, so basically a smooth function is where we can differentiate or take derivatives as much as we want. So for instance, polynomial functions, like x to the n, if we differentiate this, then we'll go down to 0, and after that, we'll just stay at 0, right? And, you know, this is all smooth and differentiable and stuff like that. All right, so that's a manifold, and notice that we haven't mentioned topology here, right? We've used continuity and differentiability, but that is coming from real analysis, right? We're working with, you know, these charts are defined as, or are identifiable as regions of Rn, but we can define a topology on M. So the topology of a manifold on M is given by taking as open sets the regions of the charts which are identifiable with open regions in Rn. And then closing under unions. So I mentioned in the last video, if you were given open sets, you can take as many unions as you want. So here we're defining open sets inside of the charts, right? But then we can generalize that by taking arbitrary unions, so we can have open sets that are on two different charts, say. So this defines a topology on M. So we're basically inheriting a topology on each chart from Rn, and then using those topologies to build up a global topology on M. So that's the suitable definitions. Now let's get into some examples that you may have seen before. So a really easy example would be, or I should say, regions of complex space. So these are the complex numbers, you know, like since we could take, right, Euclidean space Rn, this is like an n-dimensional real space. Cn is a n-dimensional complex space, but each complex space can be regarded as a real plane. So regions of Cn are 2 N manifolds. A next example is that of a non-singular surface. Non-singular surface. So a non-singular surface of dimension k is, oh, hold on, I think I know why this might be lagging. All right, of dimension k in Rn is given by n minus k equations f sub I of x1 dot xn equals 0, where the index I, so this is an I here, f sub I, where I runs from 1 to n minus k, right? So we have n minus k functions f sub I, and these are functions of the coordinates on Rn, and we're setting them equal to 0. So we have a system of equations here. So the surface is defined as the solution of this system of equations, and it's a surface of dimension k. And the non-singular bit comes from this extra condition such that if we look at the matrix of derivatives, so this is well, these are partial derivatives. So partial derivative of f sub I with respect to xj. So this is a matrix, and notice that this is a n minus k by n matrix. So it's not a square matrix, but our condition here is that this matrix has rank n minus k. And if you don't know what a matrix rank is, there's an alternative condition which I'll mention here. But essentially, this is the maximum rank that this matrix can have. Since n minus k is less than n, the rank of a matrix is limited by its lower dimension, right? So this is the maximal rank that this matrix can have. So an equivalent condition is that so imagine here, right, we have this matrix is so this is an n minus k by n matrix. So let me just and so an equivalent condition to this having maximal rank is saying that we can pick, essentially there is, or there are n minus k columns such that the n minus k by n minus k matrix has non-zero determinant. So I'm assuming here that more people are familiar with the concept of a determinant than they are with the rank, or at least for me, the determinant is easier to grasp because it has more of a computational definition, so you can just think of it like that. So what this is saying is that the columns, and remember the columns are given by the coordinates from Rn, right? So it's saying that we can pick n minus k of these coordinates and focus on those columns, and that and then we would have a square matrix. And once we have a square matrix, we can take the determinant. So that's an equivalent condition. So the charts, I won't go into the coordinate system on each chart, but the charts are given by regions U, they're denoted like this, such that the matrix where J is going from, or not going from, but J is equal to these n minus k J values. So here we're picking, right, again, in correspondence with this equivalent condition for rank n minus k, we are picking n minus k of the coordinates such that this new square matrix has non-zero determinant. And the reason why we can pick these charts is essentially because we know that we can, the equivalent condition says that we can always pick some n minus k coordinates such that the square matrix has non-zero determinant. So these regions are just regions where the specific, for those specific coordinates, it has non-zero determinant. So any point on the surface must lie in one of these regions. And so we can form a manifold structure on the surface in that way. The next important example, which you should all be familiar with, is that of the n-dimensional sphere. So the n-dimensional sphere is defined by the equation in n+1 Euclidean space, such that the norm of this vector is equal to 1, right? So the sum of the squares of the coordinates are equal to 1. So for instance, in R2, we would have the S1, which is the circle, be x1 squared plus x2 squared equals 1. Now this is a manifold, And here is really where I think the concept of a manifold becomes important, because you cannot define a single coordinate system on the sphere which is not non-singular somewhere. What this means, and you may know, like, okay, spherical coordinates, but the problem with spherical coordinates is the wraparound property, right? You're approaching from one angle, so say you have here is 0, and then you're approaching from one angle, and you're approaching 2 pi, and so there's a sort of jump discontinuity here. Okay, my computer is not having fun today. Anyway, and so it's better to use a manifold structure on the sphere. And we could do that using stereographic projection, which some of you may have heard before. So essentially, we use the north and south poles of the sphere, where all of these coordinates are 0, and then the last coordinate is either 1 or -1. And so let's look at just you can consider this as like a plane, or like just a plane cut version of the sphere, or you can just consider this as the example of the circle, but essentially, since we are limited to drawing in 2 dimensions, this is the best I can do. So I guess you could say that this up and down axis would be the n+1 coordinate, and then this line is representing all of Rn. Now, stereographic projection takes some point here, and you start at n, and you say, okay, I'm going to draw a line from n to x. It's going to cross the Rn plane at some point, and we call that un of x. Or we could start at s and do the same thing, and it will also cut the Rn plane at some point, which we call usx. And so the important thing to do is, or to notice, is that un of x we can define for any point on the sphere except for n, because if we try drawing a line from n to n, well, that's not well defined. You could say, okay, what about the tangent? But then the tangent won't intersect this Rn plane. So essentially the un of x is defined on Sn minus x, or sorry, minus the point n, and us of x is defined on Sn minus the south pole. So we have 2 charts. These are our 2 charts on Sn. And a funny thing here is that the points us and us of x and un of x, if we're considering it in this 2-dimensional picture, well, for one thing, even though we're representing this Rn, all of Rn as a line, we can actually see that this is going, the points, essentially the points 0, us of x, and un of x are collinear. They don't necessarily lie on some coordinate axis, but they will lie on some line in the plane Rn. And in fact, they are related in terms of circle inversion, which I find which I find interesting. So we know that the radius of this circle is 1, right? Because it's the unit circle. And essentially, oh dear. Okay. Essentially, the picture to see here is I'm going to, all right, so here's 0, 0, the origin. And here's S, and here's US of X. So I've plucked out this triangle from the picture just so we can see it better. Okay, so this triangle. And then I'm going to pluck out this triangle here. And so this length is 1, by the way. And then I'm going to pluck out that other triangle. This length is 1, this is n, this is the origin, and this is un of x. And so we know that these are both right triangles, and using this intermediate triangle, which that connects S, N, and X, this is length 2, this is also a right angle. So using that triangle, you can show that this triangle is similar to both this triangle and this triangle. Which means in particular that that these two triangles are similar to each other. And so this length here we would refer to as the magnitude of US of X, and this length here is the magnitude of UN of X. And so we can use triangle similarity to say, okay, 1 over the magnitude of UN is equal to the magnitude of US over 1. And so what this tells us is that the product of the magnitudes is equal to 1. And in general, if this were a circle of radius r, then here we would have r and r, and so this would be r squared. And so that's sort of the main relation for circle inversion. But putting together these two facts here, so again, I'll replace this with 1. Since we know the relationship between their magnitudes, and we know they're collinear, then we can relate, we can write the transfer, or the transition functions simply like this. So this is on Sn minus the north and south poles, right? Because the transition function is defined on the intersection of the charts. All right, so that's the second example of our manifold. Next are some matrix groups that you may be familiar with. So for instance, GL of N is the set, really group, but I'm not going to be focusing on the algebraic part of in this series. It is wonderful, and I may come back and do a series on Lie groups, but that's not my main focus for this series. Anyway, so GL of N is the set of n by n real matrices with non-zero determinant. And you can show that this is a non-singular surface in Rn squared, right? Because you consider the space of n by n real matrices as Rn squared. And you can show that this is a non-singular surface in Rn squared. So, therefore, it is a manifold, since non-singular surfaces are manifolds. There's also the special, so this is called the general linear group. So that's what the GL stands for. SL of n is essentially the same thing, but where the determinant equals 1, right? So this is a subgroup of GL of n, and this is also you can show it's also a non-singular surface, so it's also a manifold. And in particular, SL of n is a connected. It's a connected manifold. GL of n is not connected because matrices with positive and negative determinant cannot be connected by a continuous path, because if you have some continuous path from one matrix to the other, then you can project that to a continuous path in the real line between their determinants. And so if these two matrices have opposite sign determinants, then this continuous path must cross through 0. And therefore, at some point in this path, you will have a matrix with 0 determinant, which is not in GL of n. So this is not connected, whereas SL of n is. A third example of a matrix group is the orthogonal group, which are the matrices such that if you take the matrix and multiply it by its transpose, this is equal to the identity. And this is an example of a compact manifold. Oh, and I forgot to mention, Sn is compact, because, again, remember, I mentioned in the last video, by Heine-Borel, if we have something in Euclidean space and it's closed and bounded, then it's compact. The sphere is obviously bounded, and it's closed because, well, I guess it's hard to argue that, I suppose, without the use of limit points, because closedness in Euclidean space is usually via a limit point argument. But you can basically say that, okay, if I take the complement of Sn, then I'm going to have two open regions. So that's like another way to see it, I guess. All right. Finally, our last example for this video is that of projective space. And so this is sort of an example which seems weird and maybe unimportant at first. Because if you're interested in geometry, then obviously the sphere is going to have, purpose, right? We all know what the sphere is. And then surfaces obviously arise from systems of equations, so that makes sense. Matrix groups, obviously, if you're into algebra, these are very important, or even just linear algebra. But projective spaces are actually very important in their own right. And I'm only going to be covering real projective space. Oh, and that's another point. I won't be talking about complex manifolds. You can essentially define the same thing where you have charts which are identifiable with complex space. And so similarly, as there are real projective spaces, you can have complex projective spaces, but I'm only going to be focusing on the real ones, just because they're easier to talk about, but they're equally, if not more, important. So anyway, the construction of God, will this erase? Okay. The construction of real projective space is we start in Rn plus 1 minus 0, okay? And we consider, essentially, these points as vectors, right? And we're using this word loosely because we haven't, and really vectors just deserves sort of a better word here, but right, just I mean, just think of it as a set of these numbers, right? X. Actually, I'm going to use y because I use it later on. But anyway, we have these coordinates where not all of these, so this is not equal to 0. And we're just going to consider this as a vector, right? Just a vector is a list of numbers, as you might have learned it that way. And what we can do is define an equivalence relation V equivalent to W via essentially by V is equivalent to W if V is a scalar multiple of W. So C is some real number, right? So what this is saying, if we consider the real plane, right, so minus 0 here, so if I have this point 1, 1, well, I can consider it as a vector here, and I have some other, like -2, -2, right? I'm considering these two vectors to be the same thing because they're related via the scalar multiple -2 or alternatively -1/2. So essentially the space under this equivalence relation is what real projective space is. And so essentially this is just looking at only directional vectors. A different, more geometric way to look at this, or I guess I should say topological way to look at this, is if we start with the sphere, right, and again I'm just going to use a circle because we're drawing in 2 dimensions. If we start with a sphere, right, then any two antipodal, so these are called antipodal points. Any two antipodal points are going to have equivalent direction vectors, right? And we get all of the direction vectors just by tracing along Sn. So we can essentially take Rpn is Sn under the equivalence relation where x is equivalent to -x. If we're considering x here points, right, like x, y, then this is -x, -y. Or if you had 3 coordinates, you would just take the negative of all the coordinates, right? Because that's how we can represent antipodal points, since this is the origin, right? That relationship is via the negative sign. So Sn under this equivalence relation is also the real projective plane. And so notice here that we can start at this point, 1, 0, and we can trace along here, and then once we get to -1, 0, well, that's the same thing as the point 1, 0. So in fact, a funny thing about this is that this is saying that the real projective line is equivalent to, or topologically equivalent to the circle, because we just go around, and then we get here, and then we jump over back to this point. So it's actually just a circle, which I think is kind of cool. This relationship also implies that the real projective spaces are compact, because Sn is compact. So this is another way of saying this, by the way, is that Rpn is a quotient space. And so we could give it the quotient topology, which I described on the last video. But if you take a compact space and take, essentially this is a subspace of it, or a quotient space, then it will also be compact. And I was going to describe the charts and coordinate system for projective space here, but I think this video is already getting kind of long. I know the last one was really long, so I don't want to drag this on. And I also had an issue with the coordinate space I was going to introduce, because later, in a later video, where I'm going to prove that odd dimensional projective spaces are orientable, and in that video I'm going to use a different coordinate system than the one that's typically introduced. So I think it's better that I don't introduce the coordinate system now, since I'm just going to use a different one later on. So anyway, with that being said, I think this is a good stopping point. I've covered all the examples I wanted to cover, and of course the definition of a manifold and the topology on a manifold. So with all that said, I hope you enjoyed the video, and I hope to see you in the next one.